we will introduce the idea of a permutation. A permutation is simply an arrangement of objects in order. Think of it as lining things up. For example, take the three letters A, B, and C. How many different ways can we arrange them? Well, there are just a few of them, so we can write them out. One way is simply ABC, then we have ACB, BAC, BCA, CAB, and finally CBA. So we have 6 ways of arranging these three objects, these three letters. Each one of these ways is a permutation. So ACB is a permutation of the letters A, B, and C. BCA is another permutation, CBA, etc. Notice, of course, that the same letters appear each time, but the order is different. That's what makes permutations special. They are about ordering. Order matters. And I tell you that because people often confuse permutations and combinations. In a combination, ABC is just one set, order does not matter, but in permutation, ABC and CBA are completely different things. Each one is a different permutation. Now let's repeat what we just said, but in a more mathematical form. A permutation of a set S is a sequence that contains every element of S exactly once. For example, let's say S is our set with elements A, B, and C. In this case, the permutations of S are the sequences ABC, ACB, BAC, BCA, CAB, and CBA. Again, each one of these sequences is a different permutation of the set S. Now, suppose you have an n-element set. How many permutations of that set are there? We will use the generalized product rule, and let's first look at this example we have here. So we want to know how many ways we can arrange the three elements of this set. How many choices we have for the first element? Well, for the first one, we can choose A, B, or C, right? So we have 3 choices. Now, since we've chosen the first one already, for the second element we have 2 choices, and for the third one we have 1 choice. So there are 6 possible permutations for the set S with 3 elements. And indeed, if we count here, we have 1, 2, 3, 4, 5, 6 permutations. Now, generalizing it, if we're talking about an n-element set, we can say that the number of permutations is equal to n times n minus 1 times n minus 2 times 1, which is simply n factorial. So there are a total of n factorial permutations of an n-element set. Given that, something that is interesting to notice is that permutations grow very quickly. For example, if you have a set A whose size is 10, so it has 10 elements, then the number of permutations of this set is 10 factorial, which is already over 3 million. That's why shuffling a deck of 52 cards creates an astronomical number of possible orders. So far, we've thought of permutations as arrangements in order, but there's another way to describe them, which is using functions. Formally, a permutation of a set S is a bijection from S to itself. That means it's a function pi, it's usually written like that, where every element of S is mapped to exactly one element of S, and also every element of S appears exactly once as an output. So we have a set S, which is both the domain and the codomain, and we have a bijection from S to itself. For example, let's say that S is the set of elements 1, 2, and 3. Consider the function pi that is defined by pi of 1 is equal to 2, pi of 2 is equal to 3, and pi of 3 is equal to 1. This function just shuffles the numbers around. If we start with the order 1, 2, 3, we get 2, 3, 1, because 1 is mapped to 2, 2 is mapped to 3, and 3 is mapped to 1. That is the same permutation we would list as the sequence 2, 3, 1. So the arrangement point of view and the function point of view are really two sides of the same coin. Both capture the idea of permutation, which is a perfect reordering of a set.